First of all, is actually the motivations. I've been personally visiting the headquarters of BYD, NIO, and Apollo. They all expressed concerns. They have hundreds of people doing QC, but the QC also limited to testings, from simulation, hardware loop, and also different kinds of in-house testing, real-world testings, but they don't know how to start with formal verifications. And this problem also sits in the drone companies. In Australia, surprisingly, we have more than 100 companies do drones, from small drones to delivery drone to tons of cargo drones. But they also facing problem, especially landing into unmarked areas and deliver to moving targets. In Australia, we have a lot of billionaires. They have yachts. They want to deliver some French champagnes and Australian wines and seafood, but they don't want to stop. So it's landing in these moving targets is very difficult. The algorithm is easy to develop. To provide safety guarantee is so difficult. And this is actually causing a lot of crashing, Tesla crashing, autopilot in Tesla crashing into overturned trucks. And in just half a year ago, the Xiaomi SU7 crashed into a road infrastructure. People die in the cars. So why is it so hard? Looking to the spectrums, we have traditional ML, right? Of people doing populist model checking, symbolic model checking, and like Isabel, this kind of theorem proving, and runtime verifications. But these kind of things, techniques, cannot directly apply to these kind of machine learning enabled systems. This is the state-of-art industrial scale ADA systems. You can see you have a lot of sensors, multimodality sensors. You have different perception modules. Inside perception module, you have maybe 10 or 20 different kind of machine learning models. You have planning and control, localization, prediction, control majorly is rule-based. So you have this distributed machine learning and the symbolic-driven hybrid systems. Very hard to verify it. Yes, Taylor Johnson from Vanderbilt in the Shonan Seminar present the latest work from this machine learning verification community competition. They can verify right now a semantic segmentation models, foundation model, which is millions or billions of parameters, but it's still based on some bounded input-output assumption. So you have a input space. You bounded the input space to a region or to a ball, but it's very hard to translate into a real-world semantics, right? So it's very difficult. They can't verify very complex system property. They can maybe apply for left-right collision avoidance, but for system liveness and safety properties, they cannot verify it. The state-of-art ReLU-Plex is basically ReLU. They're using some solvers. Alphabet Cron is from UCLA, mainly by these people, and also UIUC. They basically based on the linear programming optimizations. They rely on the input-out properties mainly. In system-level testing, we've done a lot of testing. So we do this kind of fuzzing, search-based testings, robustness analysis, metamorphic testings. But people from community in the industry and from those formal methods community mainly think it's populist testings, right? And when I give a talk in University of Pennsylvania, there's a very famous guy called Yustin Sipoli. He gave me these very puzzling, challenging questions. James, if we rely on populist testing for populist systems, where do the safety guarantee come from? Right? This is a good question. So I want to solve these two questions separately. First of all, is populist testing. Can we make some formal guarantee into it? Second thing, for populist systems driven by AI systems, can we make it more or less deterministic? So there's two grand challenges. The first challenge is populist testing. Oh man. Okay, let's do this. Oh, sorry. Okay. I think it's fine now. Okay, so in 24 January, we start in San Diego, where the ICCPS community starts. So these are the main people who start ICCPS. They start this kind of community for TACPS. We want to revive, because in the community, in this industry, people already use testing, right? Why not make testing a lot more formal instead of populistic? So one thing we talk about is model-based testing. The model is not machine model. We'll talk about this like a hybrid model, right? State machine is kind of formal models. But this formal model, we think about something instead of from passive to active. So in runtime verifications, if you have logs, you can verify. If you don't have logs, you cannot verify, right? We want to, based on the existing log, to manipulate the perturbed logs to generate something easily pushing the runtime verify towards crashing, right? This is our idea. But we found a problem because where the model come from? People cannot write these formal specifications. Then we come to the second part. which is the model learning. In Yale University, La Luzinta CAV community, they have this L-star learning for algorithm, 1987. But this L-star learning requires coactive learning. They construct the construction tables and do the hypothesis with oracles to finally construct the entire formal method specifications. But it requires oracle, right? The oracle does not exist. And in data-driven testing, data-driven specification mining or set-based, you require a lot of data. Where data come from? You don't have data. So we have another stuck in another bottlenecks, right? So we turn into LLM. We actually later found out not only we can use LLM to generate many test cases, and we can explore many safety properties, which means we can generate a lot of logs and data. This data contains a lot of underlying lot of safety and liveness properties. And eventually we found out we even can use foundation model to get specific mining. We can get foundation model for these model-based testings. Now let's focus on these LLM-based testings for now. This is mainly our implementation in the 25-26. First of all, this is our signature paper, named called target. So the key contribution of this paper, which is TSC and presented ASC 25 in South Korea, is this contribution. So we argue for this learning-enabled CPS. If you use foundation model, large language model to generate test script, it's unrealistic because you don't have so much training data available. And because the brick wall between industry and academics, they won't release the source code to you. So you don't have enough training data sets to train the LLM. So you cannot generate test script directly. What we do is actually let LLM to learn a new languages to describe the scenario of ADS. This is our target key contribution in the DSL. Then people argue industry already have some DSL called open scenario. But that open scenario is too complex to describe a lane changing requires 250 lines. It's very hard for the LLM to learn without hallucinations. Then Sanjay Sashya from UC Berkeley said, hey, I have a DSL. That's called scenic programming languages. That's a probabilistic DSL programming languages. You can do formal applications. But the problem is that's too detailed to the level of the angle of turning, right? The lane size. But we found out for LLM to learn this numeric data to be precision is very difficult, very easy to hallucinate, turns these kind of numeric data. So we come into an intermediate infrastructure, intermediate DSL, which is semantically rich, but syntactically simple, and also compositional. So you have environment described the road environment, you have the context environment, you have road network described its intersection, roundabout, and highway. You have this actor to describe the actor present in the scenarios like trucks, vehicles, pedestrians, and you have oracle because it's running simulator. You have oracle, and then you have this one, and you're passing the traffic rules. We give the traffic rule based on the Texas because I grab on YouTube, so it's easy for me to grab it. So and then we have a Texas traffic rule given to it. And we can distill many, many important rules which can translate into DSL representation. What we do is actually compositional. Your input window, the prompt window, context window is smaller. From numerous paper from UCLA or other people, you found it more bigger the context window, easy to lead to hallucinations. So your less context window is easier to avoid hallucination. Second thing, for every single output for each component, we create a customized validation. You can automate it to do validation, to check whether the LLM has hallucination or not. So in the end, for every single traffic rule we distilled, we have a DSL representations. Then the representation, you can think that the LLM can learn a new language to describe the traffic rules, right? And based on this language, because it's structured, we can easily generate the scenario. How? Because we are so familiar with all the state-of-art simulator. There's a handful of simulators you can use in the real world. There's not many simulators you can use. UCLA have MetaDrive, and also we are right now take over LGS SVL, which named its own self called SVL, and Baidu has its own color simulator. Called Baidu Apollo simulator. Also, you have a simulator called HALA, BMG. You have handle simulator. We know this simulator. We create template for each simulator, but we leave the parameters for the scenario empty. Then, based on this scenario representation, we do a hierarchical search to find the parameter and fill in the template. You've done the scenario generation. So that's our key contributions. And if you're looking into the DSL, you can see it's compositional. right? You have environment, you have load network, your actor, and the oracles, right? It's a context-free grammar, the semantics of it. So it's very easy for the LLM to learn it and easy to validate it. And we have this knowledge validation. We also have a syntax knowledge validation. We make sure that syntactically and semantically, the DSL representation you learn for each rule is correct. Right? It's easy to verify because compositional. And once we have this DSL representation, we have template which is fill in all these missing pieces. Because you do program synthesis to generate the entire program is very difficult. It's very hard to prove correct by construction. But if the code is already there, you're only missing some parameters. It's not easy, right? It's not easy. Then how we do? First of all, we want to find from all the existing simulator maps, which node network is consistent with the description of node networks in DSL. Then we locate the maps. We locate the node network of equal vehicle, right? Once we locate the maps, node networks, we locate the trajectory, the starting point, end point for equal vehicle, then you can plant the other vehicle trajectory easily. So we can call hierarchical search. All these parameters will backfill into the function, and then you have the scripts. Right? This is the indirect, but it's very, very effective. RQ1 is to show the DSL representation learned from LLM is consistent with manually written oracle. Not one right, multiple people right. We have these statistical testings. Second thing, if you generate scenario, is generate scenario semantically consistent with original traffic rule? You have to do user study, right, to check this. The last one is utility. It's useful. Can you find some very subtle bugs? So we test on the 3 simulator we know, Kala, LG, CVL, MetaDrive. We test on different ADS, especially the Apollo and AutoWare. These are the only 2 open source industrial scale ADS systems available to test. And we test the different LLM to see the sensitivity of LLM used. We use the Texas driving handbook because the one collaborator is from Texas. And you can see in terms of the DSL learning capabilities, if we have all these verification and validation on semantics at syntactic level, you can see the accuracy reached to 98%. And you can see if without this one, the places you can hallucinate is actually numeric value. See the position relation and the position references. The numeric value is very easily for LLM to hallucinate. Later, there's a paper about it to prove it is why LLM hallucinate for numerical points. All right, in terms of the semantic consistency, when you do a user study, I teach software engineering. In Macquarie, we have 600 students in software engineering classes. So as one of the assignment to do this case study, I show them the video clips of the scenario generated compared with the traffic rule. And we give very clear instructions to see whether they match. And you can see in all the traffic rules, 18 traffic rules randomly picked, almost totally match, almost match. And people say, oh, James, this is bias use of this. So much students, right? So, and then we pay for the prolific workers who come from different parts of the world. They all have driving experiences. And you can see the evaluation results are very similar, right? Which is concur, and you have these statistical guarantees. Okay, utility. We found it interesting. Apollo 7.0 is more robust than AutoWare. They have less rule violations. They have less collision. But the issue is, these Apollo AutoWare, they all have this timeout. Timeout is actually misleading terminology. Actually, the right terminology is called immobilities. That's why the SU7 collide. What's immobility is actually one ADS system in counter scenario. The ADS system decides, I don't know what to do. And then in the Xiaomi SU7, actually we transit to manual driving. But the issue is if the driver behind the wheel is sleeping, and that happens to the SU7, and they only give her or the driver 2 seconds to respond because 100 kilometers per hour, they're not going to help anything, right? So this is very critical bugs. And we report to Apollo 7.0 teams, they have Apollo 8.0, 9.0. It seems to solve most of the problems they have for timeout or immobilities. And then we have follow-up works. Purdue teams take our exacted pipeline But instead of passing the traffic rule, they put input text and input images and publish in the FS26. I was there in the session. It's so similar, the pipeline. They're actually using target pipeline. But the difference is actually there's multimodality. And instead of generating the first suitable scenario, they do a search for all suitable scenario for the traffic rule, see which scenario can cause the crashes. And we in the ICSI this year, we have these safe papers to extend it beyond this one. How the safe paper works is this. Because we already, besides traffic rules, we know in the world, we also have this crash report. I think Gordon Fraser started this crash report analysis long time ago. But right now, the crash report has multimodality. Not only have text description, but also have sketches. So we take both in and use LLM, use the same pipeline target. We want to see whether we can learn the crash underlying DSL representation of the crash. And then using similar things to the program synthesis, template-based program synthesis to generate the scenario. We found it doesn't work. Why? Because different crash have different load networks. We found that for different load networks, your prompt template should be different. Now we're using some RAG-inspired idea to have a central repository. We pre-store many types of load networks related templates. The template is prompt template. So when you have a crash report, we do adaptive prompting. So other things is actually static prompting, but if you, depending on your load networks described in the crash report, we use different prompt templates. We found this actually significantly increased the accuracy of DSL rendered. The second thing we found, HALA simulator and the LGSVL, they are very restrictive for the maps. If you have maps, you can generate. If you don't have maps, you cannot generate. So we want beyond that. We want to generate load networks ourselves. And we found two simulators can support it. One is BMG, and that is UCLA MetaDrive. So we utilize these two. Depending on load networks, we construct the maps ourselves dynamically. That's, I think, the second contribution of the safe papers. Other things is exactly like target. Take it. And that's the key contribution. So we have this same thing, few shot prompting. We have this, but we extend the DSL. You see, we have the initial positioning, speed limit, these things to make sure we have some correct description of the trajectories, right? Just trajectories. Then the key thing is adaptive prompting. We have a database stored there. Depending on your load networks, we're using different templates. We call it adaptive prompting. Okay, then we generate the scenario. You can see we generate this in MetaDrive, we generate these things. BMG, we construct the maps ourselves dynamically, depending on the DSL representations. And in terms of the scenario extraction, I talk about DSL, learning of the crash report compared to human oracle written DSL. You can see accuracy almost go to the 80 and 100% because of adaptive prompting, right? This is actually working. In terms of the general scenario, with original crash report description, human study, you can see we actually separate that into load network alignment and behavior network. Behavior alignment. Load network is static, behavior trajectory of the vehicle. We want to see whether you regenerate something that's realistic to the world, right? So we involve the experts to do it. You can see our different rules, Now here's the crash report. Different cases, our rating is very high compared with LCTG with the state of art, using LLM to generate these scenarios. Similarly to this AC3R. I think AC3R is from Gordon Fraser's extended papers. Yeah. In terms of the ADS, we test 3 ADS systems, PPO, IDM, and auto BMG. You can see we can explore more scenarios, explore more variations. That's the number of variations we can explore. In terms of efficiency, we're using top 1, top 2, top 3 to find the first one, the first 2, first 3, how many test cases needed. Less is better. You can see compared to other things, we actually also a lot better, 1, 3, and 4 instead of LCTG and A3R. In terms of general scenarios, you can see the original sketches here, 119489 and 120423. And you can see the safe generator is very similar to original one, but the LCD gene generator is very different from the original one because they confuse with low networks, right? Which means the crash scenario is not genuine. But if you remove the adaptive prompting, you can see the accuracy significantly dropped. especially overall, right? That's the reason the key contribution of our study for the foundation model using is adaptive prompting, different case, different templates, right? And you can see the generated the DSL representation is wrong. Instead of this intersection becomes two-way streets. Okay, this is all testing. And then this the ADS, because in Australia we don't have vehicles to run on the road. We cannot extend beyond simulation to the hardware and the vehicle on the road. We are testing, but in June we can. So we have this software in the loop testing, which is using the ASIN. We also have this hardware loop to test each individual controllers. We even can fly our drones in our Macquarie parks. And we have many papers published. There's two papers I want to highlight. First is this XE paper called GAR. So why I want to sell this paper is because people talk about simulation has fidelity problems, right? One of the fidelity problems is actually in the scenario, the dynamic objects, their trajectories are predefined, which is not realistic. Because in real world, these vehicles, pedestrians, their behavior in the next second is dependent on your vehicle's behavior and other vehicle behavior, right? It's dynamic determined. But to do that in the DRL, or people call multi-agent DRL, but we all know have high fidelity DRL is very hard to converge, right? It's very hard to train. People use approximation, but you don't want approximation because approximation you will create infidel DRL agents. What we do here is actually we want to create a high fidelity DRL, but converge very quickly, 1 hour to converge. How we do that? 2 stages. First of all, this is actually inspired by the landing scenario. Our industry partner is UAV delivery company. They deliver organs to the hospitals, but they need to land into the hospital car park. But unlike in China, it's infrastructure maniac. They build all the infrastructure away. Australia does not have this facility, and the government doesn't want to do it. So in Australia, you want to deliver these things, you deliver in a market. You land to a market, that's it. But however, if you don't have safe infrastructure, you land to a market, you have to consider about collisions. Because in car park, you have ambulance, you have private cars. They can anytime collide with you, right? You don't have this safety guarantee anymore. So in here, we will think about if you deliver the organ to a car park, what you really care about is the nearby zone around the car park, right? You don't need to worry about the highways or the balcony or the rooftops. So we're using this kind of NSGA, people or multi-objective search functions to give some fitness values to reduce the search space in the C. So you can't only generate C, which you can focus on this car park area because this can give you the highest reward. And then based on this one, we can do learning. However, still the DRL learning cannot converge because your action state space is continuous and your state space continuous. Can we make the state space, action space smaller? Yes, you can, because you already know the dynamics, physics or dynamics of the drones, right? By the people you work with, they give you all the specifications. Then you make the action space discrete because you can make left, right, top, bottom, and hover, right? And you know in the given time slots, you do a left in the next time steps, how left it can be, right? You don't need the continuous. Second thing, and for the trajectory of object you observe, you don't really care about artistic feature, right? Because game engine in the end, UE4, it's a beautiful the trajectories. You don't care about beautiful. You only care about in certain time where's the position of the object. You can do discrete sampling, right? Discrete sampling. Then your observation space, state space become discrete. Your action space becomes discrete. You can do a surrogate training. That's how we did. Reduce the search space from the seed and do surrogate training. And the artistic effect is very ugly. People call it zombie jump because suddenly the object moves to another thing. We don't really care about artistic effects. I just want the truth, right? It's working. I show you. We found this tattoo box. This is super dangerous because the industry collaborators, they from the IROS and the ICRA community, they found the best performing obstacle avoidance planner, or called local planner. From A to B, you have obstacle avoidance. For this local planner, For every single obstacle you detect it, you create a safe buffer, right? Because you want to be safe. But the things they haven't tested thoroughly is if any sudden dynamic objects appear in the buffer area, the planner crash. When the planner crash, the Jackson ball hosting the planner crash, and then the RG Pirate and PX4, this control software crash, your Zheng crash. That's the reason we have people holding the Zheng using the LAN. But you have tons of Zheng. Who can hold it? There's no one can hold it. It's super dangerous. We save lives because months later they were deployed to the hospital, and we found these bugs. And in the end, we published a DSM paper using symbolic, entirely symbolic, like a rapid tree, to replace this planner. Then people talk about why it can be champion in the ICRA and EROS because they have different assumptions. That obstacle avoidance algorithm is using for championship competition. In the static room, you have all the static obstacles. Who can fly from A to the B quickest without collision is the winner. They only consider static. They haven't considered dynamic objects can appear. It's a raw assumption they cannot take. They just copy and paste. That's very dangerous, right? Like people right now copy paste from LLM, the code agent, to other projects without knowing the assumptions. It's very, very dangerous. Okay, this is the one we found. The second work in FS 26 just recently accepted. We want to push it forward. You can see this multi-objective is just polishing and filter the first C, right? But the important thing is actually when you go to the simulator can give you very good feedbacks. And this feedback can be used as iterative refining the seed to generate more dangerous scenarios, right? FS 26 is doing this work. It's called SVGD based CD refinement. S is called stand operator. V called variational inference. GD is gradient descent. It's a gradient descent things. So basically, from all the simulator, you can create a learning-based hazard model. Very easy. By the position and the heading velocity, this information, you can train approximate model to predict how dangerous is the behavior. Simulator give you all oracle data, right? You can train this model. This model will give you the differential result, which you can do gradient descent, right? Okay, cool. Then the variational inference can take this gradient descent to create a target distribution. You move the particle towards this, right? But the problem is, if every single test seed looks exactly the same, doesn't make any sense. You want diversity. The stand operator in SVGD, stand, make sure this. So they want to push the particles towards from original noisy Gaussian distribution towards target distribution, not only toward, but from different directions. That push for diversity, isn't it? SVGD is from machine learning community, we just take it. But we found this usage in here can help iteratively refine the seed, find the very dangerous driving behavior. That's the FSC 26 papers. I don't have funding to support students to go there, so I just promote here. This is the paper here. You can read the archive paper now. Okay, that's the from particles to parallels. But the important thing is actually we only solve a little bit about challenge one, from probability testing towards a lot more fidelity and some kind of conformance testing, right? But the system is still probabilistic because it has machine learning. How we can make machine learning more predictable? Neuro-Symbolic. Neuro-Symbolic has been around for 20 years or more. From my best, you know, Hamburg, Stephanie sent me a book. I wrote a book about Neuro-Symbolic 10 years ago. But when I looked at the book, I found something interesting. The Neuro-Symbolic is symbolic. Neuro creates something, and taken by symbolic input, and symbolic give decision. Neuro and symbolic, they are not tightly integrated. The neuro-symbolic in our idea is neuro should be constrained by symbolic properties, not trained by data, trained by symbolic property to be conformed. Well, symbolic can learn from neuro to be adaptive. That's the neuro-symbolic one push for. And then we look into the state of art. There's a tensor log, differentiable prolog, it's prolog derivatives. And from MIT, they have this string coder, neuro-symbolic synthesis. So the first one is differentiable symbolic AI, you can think about that. The second one is actually observe the input and output for neural networks. You can program synthesis a deterministic symbolic system. Both of them are too extreme. We want in the middle ground, which you can provide the tight integrations. based on this, we have second workshop in relay, and we pushing for this architecture. From architecture-wise, we want to rewrite architecture of learning-based CPS. So not only neuron-driven, it's neuro-symbolic-driven. I can explain in three perspectives. First of all, I said before, the special mining right now cannot rely on active learning or data-driven learning. You can rely on foundation models. Foundation models somehow can learn from data the underlying specification, but just have hallucination, right? But you have the power. If you can let foundation model to propose, using symbolic rules to verify, you actually can extract many interesting properties from underlying data. Once you have these properties, that is the second part. Industry people, they have no idea how to write formal properties, and they don't want to learn. Right? It's a huge learning curve, and they don't want to learn. What you can do, you can generate this kind of DSL-like target. The DSL for the sensor fusion, DSL for the semantic map, DSL for the word model, DSL for the global planning, local planning, and actuations. From the DSL, you can do program synthesis. You can generate two things. First of all, neuro-symbolic program. Second thing, purely symbolic program. The purely symbolic program is we call symbolic word model. You model the instance level, what you see, what you saw, into a graph we call scene graph, or called spatial temporal scene graph. In terms of sensing is neuro-symbolic, neural part provide the feature vectors, and the symbolic align feature vector to predicates, and then do decision layer using symbolic AI programs instead of software distributions. I can show you both in the later some papers. And then you can open the door for formal methods people. You can do Isabel. If the symbolic AI is first order logic, you can do field proving. You can do model checking. You can do interpretation, and you can do statistical analysis. Testing becomes a white box instead of black box. Neural coverage can be changed as well. So this is very promising, but it's a lot of difficulties. First of all, what do you mean neuro-symbolic integration? From Zheng, from UPenn, and now it's in Johns Hopkins University, we have this idea. He implemented himself with Jianing together. Is this? So from the videos, you already have the VQA, right? You have these captions. Using a lot of state-of-the-art things, you can convert the caption into a temporal logics, right? This is taken from off-shelf. And then what you do is actually you have these temporal specifications. You want to use this temporal specification to guide the training of the neural network to generate something called scene graph. This scene graph generation underlying is conformed to specifications. Okay, how they do it is simple. They use something called SG-clip, a foundation model, to generate the scene graph. But they want the scene graph not only trained by the data, but also trained by this conformance. What they do is actually they break the SG-clip into multiple modules. You have object detection models, you have bounding box, you have semantic everything. They go to object predicates, relation of predicates, and property predicates. They track the predicates window to window, whether these predicates being satisfied or not. They calculate the loss. The general scene graph, how much they are away from its temporal specifications. And using this loss, they break into three loss terms, into its object, predicates, the relation, and property, to make sure the SG-clip generates a spatial temporal scene graph, a result, which is consistent with the description of the temporal logics, which is cool, right? But the big problem is they actually doing the overall specification conformance. They don't know whether each thing is conform or not. They do a coarse granularity mapping instead of concept level mapping. Makes sense? So they do concept level, but it's not 100% no, because the conformance loss is calculated based on the entire thing. Okay. But it is promising. Okay, now I will talk about the industry engagement, which get myself into trouble. But I think I will do it again if I know the troubles. I went to Savian, which is the Melbourne companies. They doing unmanned passenger aircraft. I want to know how they build, test, verify the systems. Right, the Savian company. And then I went to the UBTech, which is humanoid robotics in the China called the Great Bay Area to compete with the Great Bay Area in USA. They create human robotics and go to Hair Robotics. They create warehouse robotics and go to Pony AI, which do ADS, autonomous driving systems, and Shunfen, which do delivery drones. Then I found very surprising things. Believe me, this is the things I found. Okay, first of all, they growing increasing reliance on multimodality foundation model for real-time decision making. They will replace the things I showed before, module level ADS towards end-to-end foundation model ADS. They're going back. They're not going to more formal and more testable. They're towards a harder black box approach. So they go reverse way. The reason is because they have strong belief in the reasoning style of AI because they provide step-by-step reasoning. They believe this step-by-step reasoning is mimic human level reasoning. It's very hard for me to convince them otherwise. Very hard. They heavily rely on the data synthesis and the larger scale simulation over systematic assurance. They believe so large generate data is test cases. But Zheng said, right? Testing cannot reveal the absence of bugs, right? That's also very hard to tell them this, so they don't buy it. Still not have GPU, I have so many data, I can generate all the data set I want. That's it. That's the underlying messages. Brute force testing dominates the industrial validations. If they have a tight raw deadlines, they don't even run simulation testing. Raw testing. That's it. Right? And then they have this very strange priority trend. Utility over safety, safety over security, security over privacy. This is told by those people, very high rank officials. They told me that's the decision priorities. And I found the gaps as well. Data governance is sharing restricted significantly in the collaborations and the lack of effective safety guardrail for multimodality reasoning modules. We don't really have this solution for the industry. We don't. And we don't even have empirical testing evidence or formal verification results on the robustness and safety of their reasoning-enabled models. On the first hand, they don't give us the models to evaluate. Second thing is actually we don't have the empirical formal verification things, and the deployment of embodied AI is very much outpacing the assurance and certification method. They are way ahead of us. People provide assurance certifications. Okay, first of all, Kung Fu bot. I have several phone conversations with Unitree 2 VP. Their Kung Fu fighting is not autonomous, it's pre-programmed. But this creates a huge misunderstanding of the general public. People think, oh, Kung Fu robot is available in the market. It's not true. People have a mistrust of it, right? This is very, very misleading. And OpenClaw. This is another clear instances. You don't have assured, a verified multi-agent system doing everything autonomous for you. How you can guarantee the OpenClaw not stealing the bank from your mom? We have the alerts. My mom doesn't have alerts. Well, yes, with everything automated. Book hotel, book hospital. That's too dangerous. And these people, industrial solution called harness engineering. I take a good look at all this harness engineering provided by industrial people I met. In the end, yes, they provide some safe guardrail, but this safe guardrail is hard-coded, linked style harness engineering, linked. And how you guarantee the workflow among multiple AI agents can be assured because you use magic to defeat magics. In the end, all software distribution, where the confidence come from, right? This is crazy in my mind, but I cannot convince them. Okay, it's a failure for me. Okay, then I do some experiments. The first experiments in hosting the Macquarie is actually we learn it's called Aloha 2-armed robotics to do very simple things I did every day in my home, cleaning dishes. The bowl, you have a sponge, you want to clean it. This is one of the state-of-art foundation model, or called VLA model, Vision Language Action model. You can see the cleaning is very superficial, right? If my wife see I clean the dish like this one, I will be fired, right? It's not going to clean it. Clean is to make it spotless. You can use it, not superficial clean. The syntax and semantics have huge difference, isn't it? For the clean. Second one, this one, called the RDT1B. It's also a state-of-art VLA models. And you can see 2 arms have a synchronization problem somehow, and you don't know why. Yes, some people maybe can do much better job than my students, right? He only spent 8 months. But students, they have more GPU, you can run more millions of episodes, it can be better. But my question is how we can debug it. When students have this problem, Zheng, the only thing I can do is change environment and fine-tuning it. What do you mean fine-tuning? Run more episodes. We want to know where in the component failed. I want to debug it. In our software system, we can debug it, right? Step in, step over. There's nothing you can do about it, right? This is dangerous. The last one is even more ridiculous, which is called OpenVLA, which is another state-of-art VLA model. And you can see, yeah, two arms synchronized perfectly, but the right arm, it cannot grab the sponge anymore. Because we have a strong belief, our hypothesis, in the latent space. The dimension of the sponge in the latent space is very different from the dimension of sponge in the real world. The dimension is misalignment, right? But we don't know, we can't debug it. That's all because of black box. Then I have before USI visiting Lugano in parallel, I visited these two very example universities. Paris Saclay has this lady, very well respected, Isabella Gomes. She has 2 hours interrupted discussion with me when I give a talk. And in her belief, I think a lot of people doing AI is believe the general AI should not be curbed by symbolic AI. Let it grow. Symbolic AI can only create a lot of problems, does not work, does not scale, does not adapt. Once you have sufficient data, sufficient enough the power, everything problem can be solved. That's a magical word. University of Oxford, people working on this verification, Marta, Dave, we call it symbolic prism, the populist model checking, Alexandre Abbé doing this one, they believe in logics and formal methods. This is in the perfect world. Perfect world, magic world, they have collision. Magic world, everything magical happen. Perfect world, everything should be ordered. But now things working. Because from the perfect world, we cannot verify this system. From the magical world, I can't have the formal safety guarantees, or only testing. But testing cannot review all the facts. The testing, by the way, is different from our testing. The dataset testing is very different from our testing. Okay, now I have some learn from this one. First of all, people really support this kind of neuro-symbolic things, but we have a lot of problems to solve. Label intensive of the DSL. Do you have completeness and soundness from the perfect world? And from the magical world, do we have adaptability and realism? And from magical world, again, do we have magical world and the perfect world together? Do we have runtime and cost efficiency? And all together, you need the theoretical frameworks. I can't solve this problem by myself. So we have this first try to bridge the gaps. Let's create for the Zheng landing company in Australia, and they have camera, down-facing camera. They want to deploy to a scenario, you don't have marker, you can land. Right? This is difficult because you want to have safety guarantee. Because without safety guarantee, this startup company will bankrupted. They can't go to IPO stages. Right? Okay, now what we do. First of all, we use a foundation model to look at the camera image they captured. We use foundation model to create semantic everything. Okay, that's all neuron, right? Foundation model. But we do not trust the result of it. We want to do interpretation. We don't want foundation model to give the landing side. What we do, we intercept it. In here, we believe because you have so many trained data, this semantic segmentation has a lot higher confidence over predicting the safe landing site, right? Okay. From here, we can do a lot of semantic coding to get their confidence over these semantic semantic areas. We can create those person, we can figure out their relation, left and right, above, right? We can figure out their properties. Then we can, using purely symbolic methods, to generate this called probabilistic semantic scene graph. This is a symbolic structure because you can see everything here, symbolic. You can debug, you can track it, right? Because you can see from images from here, you can see where's wrong. Tree, yes, tree is here. If you say bush, it's not correct. You can easily see and debug it, okay? Once you have this scene graph, you run this scene graph with the logics in the simulator to give decision making. Then you can involve the human to synthesize the rule engine. The rule engine can execute on scene graph to find out which area is suitable for landing and why. I give you the reasons. But this is the all pipelines, okay? How we did it is this. So Scene graph generation is okay, right? I just talk about how the rule is synthesized. Okay, once you have images, we take like 72 different landing sites, and we constructed the scene graph, which is offline, symbolically. People can verify the scene graph is correct or not. Once you pass stages, use LLM. LLM is powerful now. In magical world, they can magically give you a lot of rules in the form of the scalar. Scalar is a differentiable Poirot. They can generate a lot of fantastic Poirot rules. And once you generate Poirot rules, you run the rules against the scene graph for the images to get the landing site decisions. And for each landing site decision, you give the top rules activated. And human look at it. Does it make sense? If it does not make sense, human can provide, update, delete, remove this kind of prompt in natural languages. And going back to this prompt engineer, give you the new prompts to give the LLM say you are wrong. This part is not correct. This part should be amended to generate the new batches of scaffold rules. Sometimes, at the worst case scenario, in our test scenario, in the 72 scenario, only 2 wrong we can convert to a golden oracle rule engines to determine where is a suitable landing site. This is how we synthesize the rule. Now you have the symbolic structure. You have a symbolic rule engine. How they work together. This is the rule we generated. So landing area is paved area as a dirt and the grass. They are all suitable landing area because there's all conditions, right? If it's a hazard, if the landing area is water, the landing area near the water is dangerous. You can see all these rules generated by LLMs. The hallucinatory rule can be eliminated. The good rule is being kept. You have all these rules. Then you have rule engine, you can do testing. We test on entirely different landing sites, very different data sets to test it. Okay, we compare with the industrial baselines they selected. Safe UAV is lightweight, convolution-based landing site detection. They detect all these landing sites suitable. Clearly, it's not the case. You can collide with the people, right? Peace, on the other hand, I think it's vision language model based, which is state-of-art. I said industrial people like it. 3.5 VRM based, also select these kind of things. You have Neuro-Symbolic length. We select all this one, but I will tell you we have another process to filter it. And LLM explain is another one. That's very strong VRM. They provide the safe in the middle, but the reasoning, as multi-step reasoning is wrong. They said the chosen area is an open grassy region. It's not grassy, it's sailing. It's a concrete floor, right? Hallucinated in the reasoning, but happen to find a good position, right? This is random. And then you have a semantic optic flow, which is using the pixel level tracking. This is another state of art. And they found these places. And rules can be machine specific. We can say whether it's a safe, whether it's emergency landing or rescue. Depending on mission, we have different rule set activated. If it's safe, for all these one, we select these 2 only. For emergency, in the middle. For the rescue, close to people. It's mission specific. And the foundation model is very hard to reach this mission specific. And we give reasoning. Hazard near person activated across 9 windows. Hazard near obstacle activated 4 windows. Hazard near wall 4 windows. I give you the rules why I'm not selecting this, I select that. And if you can translate this from this kind of practice to human readable English, it's very easy for people to know why you're doing this. Right? This is interpretable, explainable, and it's first order logic because scallop in the end is first order subset of first order logic. You can run Isabel. It's for theorem proving directly. Okay, now we have Shonan. With this one, we come to Shonan. I met these people from different parts of the world, not only software engineers, but the people from robotics, formal methods, lawyers. We come to this beautiful scenario called perfect world, magic world together. And then we have this Shonan with the Mount Fuji. Okay, the first insight. There's many insights. I will direct you to the technical report, which already released. I talk about 3 insights I'm personally feel interested. First of all, neural coverage to semantic coverage. We all know testing. Neural coverage gives you uncertainties. It does not reflect the semantic behavior, safety risk. It does not have any reasoning failures. It's all probabilistic. But if you move from neural coverage and pixel perturbation towards semantic coverage, you can cover unsafe and overtaking, yielding conflicts, landing zone ambiguity instead of active neurons. So you can write certificates. These examples I have covered. This is assurance, a lot better than 99% neural coverage. Right? This is direction I put. I want to establish the symbolic reason and semantic coverage-based testing for embodied AI. That's the first thing I'm very excited. Second thing, guardrail foundation models. We don't have solution yet for the industry to guardrail their foundation models, but we can. So instead of hallucination, inconsistent word model, we can use DSL, RAG, symbolic constraint, traffic rule, sync graph as a neuro-symbolic guardrail to check. We can let foundation model to propose, to wield the magic wands. It's magician. But the result will be checked, verified, and the safety guardrailed by these symbolic things. Right? Protection of it. So we let foundation model generate symbolic, verify, and repairs. I want to create something called symbolic grounding foundation models. I think that might be the solution industry will take it. You are thinking, you talk to industry, don't use foundation model. They say, no, James, no. Foundation model is really good. They're fantastic, but they just need the safe guardrail. Right? That's the symbolic grounding foundation models. The last one is verification in the foundation model era. Verification, we all know, they require determinist logics and explicit semantics. Foundation model break both assumptions. New direction is actually the specification extraction, invariant generation, oracle synthesis, and the counterexample explanation. Then we want to use foundation model, symbolic verify, runtime model together to provide continuous assurance for embodied AI. So I want to do this called neuro-symbolic compositional verification. We want to do something. It's actually we create architecture code. It's correct by construction. When we synthesize this code, neuro-symbolic code or symbolic code, from the design time, synthesis time already verify some of the property hold true. It's correct by construction. Actually, we can do it. Because neural network can already verify semantic segmentation models. But that's only limited robustness. But this local robustness, taking into symbolic, you actually can do some verifications, composition verification. These are the things we want to try. So these people, heated discussions, I was, oh my God, they're discussing about the word model. People from Yale, it's lost Professor Scott, from CAV community, Lucinta, from control theory from UCLA, Paolo, and from Washington, Sanjoy, and from UT Austin, real-time system, and from formal verification, Daniel. We have different interpretation of word model. Everyone has a different definition of word model. But we have taken very good photos together, which is fun. Thanks for our collaborators, and thanks for those things. And I think the paper is available in here. If you want to take a screenshot, you can read this paper. I cannot read this paper myself because I'm under, I'm not supposed to outside Australia. Let me put it this way. So you can read this paper here, and the paper is ready. A full technical report, not only 3 parts, but other aspects. Probably you will be interested. And yeah, that's all my talk. Thank you so much.